Hi everyone, and welcome to my capstone presentation. The goal of this project is to see if we could use machine learning algorithms to significantly speed up the runtime of GOSPL simulations, or perhaps use them in other ways. GOSPL is a Python-based numerical model that simulates global landscape dynamics over the timescale of millions of years. As inputs, it takes the initial height map of a planet such as the Earth, along with tectonic uplift and a rainfall map. It then simulates the evolution of the topography over millions of years, and it uses various erosion algorithms to do so. The model was developed by Tristan Salles, who is one of my supervisors for this capstone. This work was initially inspired by Gurin, where they trained a UNet model in the context of a generative adversarial network to generate landscapes based on sketches of rivers, crest lines, and altitudinal cues. Their model produces results within a few tens of milliseconds. In addition, I also took inspiration from a paper by Prof, where the authors used graph neural networks to significantly speed up the performance of mesh-based simulations by 2 orders of magnitude. In the discussion, they claim that their framework could potentially be used in a large variety of fields, including geophysics. To begin with, I will briefly cover some fundamental theory in supervised machine learning. You begin with a data set of example features or inputs and targets. You have a model F that takes example features as inputs and tries to make predictions that resembles the targets. You also have a loss function, like the mean square error, which measures how wrong the model is. Then, one example at a time, you make a prediction with the model, measure its loss, and use gradient-based methods such as Adam to nudge the weights into a direction that decreases the loss. Our work makes use of the UNet model, which is a fully convolutional neural network. They are popular for processing images, but they can operate on any grid-structured data. Although our data is not an image, treating so will simplify the explanation. In a single image convolution, you have a convolutional kernel matrix, which traverses over an image pixel by pixel. It then takes the dot product of each pixel's neighborhood and the kernel to form new pixels for a new image. In our context, the values of the kernel will form the trainable weights of our model, and we will be using hundreds or thousands of convolutional filters. To get an intuitive understanding for image convolutions, here are some examples, including Gaussian blur, sharpen, and outline. A single convolutional filter can effectively only operate on nearby pixels, and they cannot make use of global information available on an entire image. To solve this problem, we will be using a max pooling layer, which basically reduces the resolution of an image by returning the maximum of neighboring pixels. Any convolution done after max pooling will then have twice the reach compared to the original image. To return back to the original image resolution, we will be applying a few unpooling layers, which basically just duplicates pixels to increase the resolution. The UNet model has an encoder and decoder stage. The decoder works by taking an input image and applies multiple convolutions with kernels of trainable weights. The resolution is then decreased by max pooling. Then we have a few more convolutions and repeat until we have reached the bottom of the UNet. Notice that because the bottom filters operate on low resolution grids, they have much more global information available to them compared to the earlier convolutional filters. The decoder works by increasing the resolution with an unpooling layer, concatenates the data from the decoder of the same depth, applies a few more convolutions, and this process is repeated until we have reached the original image resolution. Because each convolutional filter returns its own image, and we have multiple filters on each layer will return a third-order tensor where the images are stacked along the third dimension. Our model requires a lot of training examples to learn from. To generate the data, I have used Perlin noise with multiple noise frequencies to define the initial elevations of the terrain and a tectonic uplift map. These randomly generated inputs were then used to run many GOSPL simulations for 60 million years with time steps of 1 million years. Over 4,000 training examples were generated in this way, with each example containing about 60 GOSPL iterations. The easiest way to greatly improve all of our results would be to improve the generation of the training data. As of now, all of the training data was generated with fixed noise amplitudes or frequencies, and rainfall was defined to be constant over the entire planet. We could also include horizontal tectonic plate movement and negative uplift to represent submersion. As of now, I've been focused on improving the machine learning models, but a model is only capable of learning based on the data that is presented to it. GOSPL operates on an icosphere, which is not compatible with the UNet model. To solve this, I have interpolated the data into a UV sphere, which can then be unwrapped into a flat image-like grid. Originally, I was using SciPy's built-in interpolation algorithm, which would have taken 30 days to interpolate all of my data. Since the distances between the vertices of our mesh is consistent within all of our data, I managed to significantly optimize the interpolation algorithm by pre-computing all distances using KD trees, pre-computing all barycentric coordinates, and then applying the interpolation. This then took about 8 hours to interpolate. In the beginning, I was following Eric Guerin's paper to build my model. Here they trained the UNet model in the context of a generative adversarial network, or GAN for short. In a GAN, you have a generative model and a discriminator model that tries to distinguish real training examples apart from fake generated ones. The loss function of the generator is based on how successful it is in fooling the discriminator, and both models are trained at the same time. This works great for randomly generating plausible examples, but GANs are not great at producing deterministic outputs such as GOSPL. When you look at Guerin's data, you can see that given an input, there are many plausible landscapes that could be generated based on the cues given. Meanwhile, in GOSPL, there is only one correct result given our input parameters. Instead of using a GAN, I found much better results when training the model with a simple mean square error loss. After interpolating our data, this is what it looks like on a flattened image-like representation. In our input features, red represents the initial elevations and green represents the tectonic uplift. In our targets, red represents the final elevations and green represents the erosion deposition, which is how much soil is deposited or removed from the landscape. Note that in this image representation, the data has been normalized to values between 0 and 255 to make it compatible as images. In our actual model, however, the features are first normalized to fit the standard normal distribution in the first layer of our model. Our model outputs the data in an unnormalized format, but our loss function normalizes it before applying the mean square error. Normalization ensures that all parameters are being treated with equal weighing in our model. Here's a summary of all the layers that I have used for the UNet model, and to the right we have the output of an untrained model. I have used ReLU as activations because they do not pose upper or lower limits on their outputs. In our first model, I have only used the first and last GOSPL iterations in the training data, giving it a time step of 60 million years per prediction. Here are the results of the model after training it for 76,000 epochs with 2,500 training examples. In the top two images, we have the ground truth targets, and at the bottom, we have our model predictions. On the left, the input data was included during training, and on the right, the data was not seen during training. As we can see, the model performs better on already seen data. This is an example of overfitting, which can be fixed by increasing the number of training examples. The model was trained and tested on an RTX 2080 graphics card with 8 GB of dedicated graphics memory. The model takes about 40 milliseconds to make a prediction after it has been set up and loaded onto the GPU. This is significantly faster compared to the 10 minutes it takes to get results with GOSPL. If we include the time it takes to set up the model and load the data onto the GPU, then the model takes about 1.5 seconds to produce a prediction. I then reduce the time step of the training data to 1 million years, which is equivalent to the smallest time step capable by GOSPL. This allows us to make a series of predictions over time. Initially, after using mostly the same code as before, the heights of the landscape blew up after 15 iterations. I analyzed Tobias Pfaff's paper, who used graph neural networks to make time series mesh-based simulations. In their work, their model was not directly predicting the final mesh parameters, but instead it was predicting the change of the parameters at each time step. After implementing this change into my model, I got much more stable results, although the landscape themselves still do not compare well compared to GOSPL. Our resulting landscape still blows up after about 200 iterations, which is well after the 60 iterations that the model was trained on, and they also don't blow up as severely. This is because the mountains eventually grow to heights that are well above the maximum height included in our training data, and so the model has not learnt how to deal with such large heights. This seems to suggest that we need to include training examples with heights well above and below the heights that we actually wish to simulate. In machine learning, time series data is commonly learned with recurrent neural networks. Here the output of a model is fed directly back into the input of the next time steps, and the weights are adjusted based on a time series of predictions. Long and short-term memory layers are a popular kind of neural networks, and TensorFlow does have long and short-term memory two-dimensional convolutional layers, which my time series model could benefit greatly from. However, after trying this, the model requires significantly more GPU memory compared to what I have available. Potential solutions could include reducing the cell's memory to 4 or 8 GOSPL iterations, or reducing the number of convolutional kernels in each layer. I could also try to only apply recurrent layers to some of the convolutional layers instead of applying it to all of them. Another issue with our current model is that it can only operate on a fixed resolution sphere. Tobias Pfaff proposed using graph neural networks to simulate mesh-based simulations. Their model can operate on any mesh-structured data, which means we could train the same model on low and high resolution meshes. Graph neural networks operate directly on graph-structured data. As input arguments, they take node parameters, and their connectivity is represented by edges. They generally operate on the concept of message passing, where nodes or edges of the graph pass their data to their neighboring nodes or edges, and this data is then updated in some trainable manner, making use of weights. In Pfaff's model, they used a multi-layer perceptron with one hidden layer as their updates. Graph convolutions are another popular method for updating the data, which can be thought of as using a multi-layer perceptron with no hidden layers. Since the source code and data of Pfaff's implementation is publicly available on GitHub, I had a go at reusing it, although so far it has not been bug-free. Using the PyTorch geometric library, I've also had a go at my own implementation of graph neural networks. To test it out, I only used the first and last GOSPL iterations as training data. The model uses 4 graph convolutions followed by 2 fully connected layers, with each hidden layer having a dimension of 128. Normalization was done similarly to my unit model. RoyalU, atom optimization, and mean square error was also used. Unfortunately, the results were not great, and the final landscape ended up looking very similar to the tectonic uplift map used. When using graph neural networks in this way, vertices are only receiving data from a small neighborhood. When looking at Prof.'s data, we can see that most of the node's parameters can be predicted based on its neighboring nodes. For example, the momentum of a node on a flag can be predicted based on the momentum of neighboring nodes. In GOSPL's case, we cannot make this assumption. The amount of soil being eroded at a particular point depends on how much water is flowing through it, which then depends on the rainfall and topography of very distant vertices. Potentially, I could try to solve this by decreasing the time step to 1 million years, making the change of parameters more gradual, but I don't feel confident that this would work. In an assignment for large-scale networks, I had a go at using graph neural networks to replicate the unit model architecture but on an icosphere. This would also allow us to use multiple resolution spheres during training and prediction. To motivate this idea, notice that an icosphere is generated by means of subdivisions. You start with an icosahedron, and on each subdivision, you add new vertices on the center of the edges. You then redefine the edges to form triangles. Notice that for every new vertex added, it has exactly 2 direct neighboring vertices that belong to the previous subdivision icosphere. This will allow us to create pooling and unpooling operations. To then form the unit-like architecture, image convolutions can be replaced with graph convolutions. Max pooling can be replicated using directional message passing to the vertices belonging to a lower subdivision icosphere, and unpooling can be replicated by directional message passing outwards. If we can get this to work well, then the very same model could be used on any graph or mesh that has been created by means of subdivision. As far as I'm aware, this has not been done before and therefore could be a very influential paper in its own right with many applications outside of just geophysics. However, pursuing this idea would be an entire research project in itself and outside the scope of this current project. We would really have to dig deep into the fundamental theory of what makes machine learning work in the first place. Based on my results so far, it seems that the traditional image unit with a single time step of 60 million years is giving the best predictions, and the time series unit model could further be improved by making good use of long and short-term memory cells. To explore the generalizability of the single time step unit model, I have tested it on input data that was generated completely differently to the training data. Here I used the Sculpt tool from Blender to draw an uplift map, used some of Blender's noise algorithms as inputs, and created an input based on Earth's historical landscapes. As we can see, the model does not always generalize well. The problem is that all of our training inputs were too similar to each other, and all inputs were generated using the same Perlin noise algorithm with the same noise frequencies and amplitudes. Machine learning models are only capable of learning from the data that is presented to it, so even the best model will only be as good as the training data that was generated for it. The easiest way to improve all of our results would be to create new data with much more diverse inputs. I should randomize the noise frequencies and amplitudes of the input noise, Even if some of the noise distributions might not resemble real Earth, it should still be included just to make the model more stable. Blender also has a diverse range of noise tools that are accessible by Python code, which is something I could take advantage of. In addition, I could create alternative algorithms to generate inputs. On Earth, most of the tectonic uplift and submersion only appears near plate tectonic boundaries. To replicate this, I could randomly generate lines, calculate the distances that vertices are from those lines, and pass those distances through a Gaussian curve. This would have a similar effect as randomly drawing lines with Blender's sculpting tools, and it is something similar to what I have already done in my last year's capstone project. While I'm at this, I should also make sure to include random rainfall maps and include negative uplift to represent submersion of tectonic plates. Badlands is a Python-based module similar to GOSPL, and it is also developed by Tristan Salles from our schools. But it operates on flat terrains rather than on round planets. If our training data was generated with Badlands instead, we could create training examples where all the examples have the same resolution, but representing different spatial distances. This would allow us to use the standard UNet model, but with differing spatial dimensions. In conclusion, there are still obvious room for improvements in the generated landscapes. However, since a single prediction only takes 40 milliseconds to produce, this speedup would allow for interactive workflows in terrain authoring, where a user could essentially get immediate results. Blender has a built-in erosion tool, but it literally takes a few minutes for it to run compared to our 40 milliseconds. And it has less features and erosion types compared to what GOSPL or Badlands has to offer. Thank you guys for listening, and have a good one.